400 million years ago, during the Devonian period, the waters were not a tropical paradise for early fish. The rivers and estuaries were murky, silt-choked environments where primitive, jawless fish were actively hunted. The predator dominating these waters was an 8-foot-long sea scorpion known as Jaekelopterus. It would lie in wait on the river bottom, a massive, multi-legged arthropod ready to strike. Looking at this modern scorpion gives you a baseline for its anatomy, but the scale is completely different. While today's arachnids fit in your hand, Jaekelopterus stretched out to over 2.5 meters long. We know this because of fossilized remains like the ones you see here in the rock. Paleontologists discovered an isolated claw fragment measuring 46 centimeters long, which allowed them to calculate the animal's massive dimensions. To understand how an arthropod reached the size of a modern crocodile, we have to look closely at its biology. A creature with an exoskeleton simply should not be able to grow this large without collapsing. Look at the thick, armored exoskeleton of a modern lobster. These heavy, calcified shells severely restrict how large a crustacean can grow. The sheer weight of the armor, combined with the immense metabolic energy required to molt and grow a new shell, puts a hard ceiling on their size. Curious Jaekelopterus bypassed this biological limit entirely. Instead of thick armor, it possessed a surprisingly fragile, paper-thin exoskeleton that lacked heavy mineral deposits. This diagram shows how that structural trade-off worked. While a dense shell sinks and requires energy to move, a thin, unmineralized shell is easily suspended and supported by the natural buoyancy of a freshwater river. This allowed the animal to increase its volume without taking on crushing mass. By shedding the weight of heavy armor, the creature also maintained its agility. Rather than lumbering along the bottom with a sluggish scavenger, it could dart through the water column and quickly change direction. It sacrificed physical defense to maximize volume and speed, creating a highly mobile aquatic hunting machine. Hunting in a Devonian delta presented a major physical challenge. The water was filled with silt and debris, dropping visibility to near zero. Tracking fast-moving fish in these conditions required specialized equipment. The creature solved this with a unique optical array. Its eyes were built with massive 70-micron photoreceptors, the light-capturing cells, which are dozens of times larger than those found in human eyes. We see this exact same eye structure today on the modern horseshoe crab. Studying this living relative helps us understand how the extinct giant processed visual information. These massive photoreceptors weren't built for high resolution, but to sharply define the edges of moving silhouettes. Combined with tactile hairs detecting physical vibrations, a complete sensory picture forms, integrating visual depth perception with physical water currents. This multimodal sensory mastery created a complete detection bubble around the predator, allowing it to strike precisely in environments where its victims were effectively blind. When a target entered that sensory bubble, the ambush was explosive. The sea scorpion lunged, snapping its elongated, scythe-like frontal appendages forward through the silt. These appendages didn't function like the heavy, crushing pincers of a modern crab. It comes down to the physics of biological levers, specifically a concept called mechanical advantage. This schematic illustrates the difference. A crusher claw uses a slow, high-force pivot. Jaekelopterus utilized a harpoon joint, sacrificing crushing power for maximum velocity. Its scimitar-shaped spikes would instantly puncture and hook into lightly armored prey. The biomechanics turned its arms into a high-speed snare, engineered to snatch primitive fish out of the water before their nervous systems could even trigger an escape reflex. This method of hunting was incredibly effective. For millions of years, these giant sea scorpions dominated the estuaries, and that constant predatory pressure actively shaped the biology of everything living around them. We can see the forensic proof of this ancient conflict in the fossil record. Paleontologists have uncovered the armor plates of early jawless fish that bear specific paired puncture wounds, perfectly matching the spacing and shape of pterygoid claws. Being constantly hunted by 2.5-meter arthropods forced these early vertebrates into a biological arms race. Here we see the result of that pressure. Early fish evolved massive upgrades to survive. articulated jaws capable of biting back, much thicker dermal armor plating to deflect harpoon strikes, and radically larger body sizes to match their predators. This led to a fatal biological irony. The same paper-thin, unmineralized exoskeleton that allowed Jaekelopterus to grow so large and agile now left it utterly defenseless against bone-crushing jaws. By perfecting its role as an apex predator, the giant sea scorpion had inadvertently forced its prey to adapt, forging the very fish that would eventually drive it to extinction. In the long timeline of evolution, today's apex predator is often just the training mechanism for tomorrow's ruler.